A while ago I finally changed this connector here, both the board-mounted header and the plug. Inside the plug, each wire is connected to a small metal contact like this. I crimped and soldered the new ones onto the ends of the wires. That's now completely solved the problem with the intermittent connection to the voltage regulator. As you'll have noticed earlier, this Spectrum is fitted with a Spanish version of the ROM. The ROM is this IC here. This was fitted as part of an earlier repair. However, this is a UK version of the Spectrum and has the UK keyboard, so its owner would like, if possible, to restore it to the correct ROM version. Now, I haven't a spare UK ROM that I can fit. However, I plan to replace that ROM with this. It's an AT27C256 one-time programmable ROM. The ROM in the Plus 2 is a 32 kilobyte device. One half of it contains the 48K mode ROM, which is almost exactly the same as that in the original Spectrum, and the other half contains the 128K operating and programming environment. This is the pinout of the one-time programmable ROM. I've put it this way around because it matches the way the ROM is installed in the Spectrum. The pinout exactly matches that required by the Spectrum, and so of course that of the original mask ROM, apart from pins 1 and 28. Here pin 1 is labelled VPP, that's a programming voltage, and that's connected to a higher voltage during the programming process. And the main 5V power supply is provided on pin 28. And the mask ROM requires the 5V power supply on pin 1, and pin 28 isn't used. However, this programmable ROM should have pins 1 and 28 connected to 5V once it's been programmed and is in normal use. So all I need to do is to install a wire across the top of the IC to connect these two pins together. I suspect that pin 28 on the socket isn't connected to anything. However, should I find out that strangely it is, all I need to do is bend up or perhaps cut off part of pin 28 on the new ROM so it won't make contact with the socket. It turns out that very helpfully, pin 28 of the ROM socket that was unused by the original ROM is already connected to the 5V power supply. So I can simply plug in the newly programmed ROM and no modification should be needed. And I'll switch on the power. There's a further modification I'd like to make relating to the audio output. All 128K versions of the Spectrum have two mechanisms for generating sound. There's the single-bit D to A converter in the ULA that all Spectrums have had, and then there's the additional AY series sound generator IC. The way the outputs of these two are combined means that the volume of the two is not equal. For example, this program here will generate a series of alternating tones of more or less exactly the same frequency, one generated by the ULA and the other by the AY sound generator chip. Hopefully you'll be able to hear that the two are not the same volume. I've also connected the Spectrum's audio output jack socket to the television, and if I switch the television to use that input instead, you'll hear that the difference in volume is even greater still. In fact, the AY generated audio is barely audible. This section of circuit diagram shows the audio connections. This is the ULA, and its audio output is here. It's connected via a coupling capacitor and a resistor to the input of the audio carrier generator. the output of which is fed to the RF modulator. The output of the AY sound chip arrives here and is added to that signal via another coupling capacitor and resistor. The ULA's audio output is also fed to the output socket on the rear of the computer via this path, through, you've guessed it, another coupling capacitor and a resistor. The AY generated audio is similarly coupled to the output socket. The audio output from the cassette player arrives here and is connected via another coupling capacitor and resistor to the audio output socket, and is also fed to the audio carrier generator via this path through this coupling capacitor and resistor and down here. After referring to some notes I made during a previous refurbishment of a Plus 2, I've changed the values of 5 resistors in this computer. I've marked the new values in pencil on this diagram. I recall I arrived at the new values by informed guesswork and experimentation. Down here, R37 has been reduced to 2.7 kiloohms and R45 increased to 33 kiloohms. And up here, R38 has been reduced to 5.6 kiloohms. These changes adjust the balance of the volume level between the ULA generated and AY chip generated sound, both at the audio output socket and that fed to the audio carrier generator. I've also substantially increased the value of R80 here from 10 kiloohms up to 270 kiloohms, and the same thing for R60 here from 68 kiloohms up to again 270 kiloohms. These two changes reduce the volume of the audio from the cassette player that's fed to the output socket and to the carrier generator. It's useful to be able to hear the audio from the cassette when software is loading, but I find it a bit distracting if it's too loud, and I prefer the balance with these changes. The television is using the signal from the computer's RF output, and I'll run this program again. The difference in volume between the two audio sources is now far less than it was before. It also sounds as if the two tones aren't as close in frequency as they ought to be, if the basic programming manual is correct. I suppose this isn't too surprising though. Perhaps my perception is also affected by the two having different harmonic content. They certainly aren't very pure tones. I'll now switch the television to use the signal from the computer's audio output socket. The overall level is reduced a bit, so I'll turn up the volume. But again, there's far less difference in the level between the two tones. Here's the cassette mechanism. It looks as if this metal bracket that holds the keys can be removed by taking out a screw here and another one here. Once that's done, the keys themselves I think can be removed by taking off this clip, and then this metal rod that supports them can be slid out. I've removed the keys. The broken ones could be unclipped from the rod quite easily without removing that, but it seemed I was going to break the other ones if I tried to do the same, so I did have to slide the rod out. All of the force of pressing the key has to be borne by this narrow point here, an obvious weakness in the design. Clearly glue is going to be involved in the repair, but I think whatever type I use, it won't be sufficient simply to glue the broken part. Some form of reinforcement is going to be required, and that'll have to be on this outside because the inside rides on the metal rod. I've reattached the two parts here using a tiny drop of superglue. That seems to have made a surprisingly strong bond, but I shouldn't think it'd stand up to much use. So I'm going to reinforce the joint by using a 2-part epoxy glue to attach this small reinforcing bracket that I fashioned out of a piece of sheet steel. It'll go on like that. And of course here's the other one that I did earlier. While I have the glue to hand, I'll also attempt to reattach this small plastic pillar to the upper case half here, where it will retain one of the screws that holds the case together. Once the glue had set, I've painted both pieces of metal with a colour that's turned out to be an almost perfect match for that of the plastic keys. So, I think I can now go ahead and reassemble all of these parts. While the paint was drying, I did quite a lot of work on the cassette mechanism. I removed an awful lot of fluff from it, and a great deal of what I think had once been a light grease but had turned into a thick glue that was present on almost all sliding parts of the mechanism, so I've cleaned away as much of that as I could, and have replaced it with a small amount of white lithium grease. I note now that when I press the play button, for example, the pinch roller moves all the way in and contacts the capstan, which it often didn't do before. It got stuck about halfway, but that seems to be working perfectly now. The pinch roller itself was absolutely caked with oxide that had flaked off cassette tape over the years, so I've cleaned all that away. And on this side I've replaced both of the drive belts. The originals had gone stiff with age and were no good at all. For the smaller one I've had to use a replacement that's slightly thicker than the original, but the new one seems to work perfectly well. Here are the sizes of belt that I've used. Now the cassette mechanism's working, I've turned my mind to a request from the owner of this Spectrum, and that's to add some means of connecting an external audio source to it for the purposes of loading software. So that might be an external cassette player in place of the built-in one, but probably more likely a mobile phone or laptop computer, etc. My first thought was to add a new socket that disconnects the internal cassette player when a jack is plugged into it, and then feeds the external audio source on into the Spectrum in place of that from the internal cassette player. But this would probably mean drilling a new hole somewhere in the case to mount the socket, or finding somewhere else to fit it, which could likely be a bit messy. So we've both agreed it would be best not to modify the case, and instead I'm going to have a look to see whether it would be possible to modify the existing audio output socket over here to behave in the same way as the audio socket on the later Plus 3 Spectrum. This is a page from the Plus 3 manual, and as you can see here, it uses a stereo audio socket to provide an input and an output combined. To that end, I've already desoldered this socket here, so I should be able to remove it. Now I suspect it's a mono socket, but let's have a look and see. This is a stereo jack plug, so I can plug that into there. There are 3 terminals on the underside of this socket, so now I can simply make some continuity checks. This terminal on the plug is connected to the tip, and to this other terminal to the centre ring, which is not connected to anything. So I suspect these 2 terminals here are simply connected to a switch mechanism that connects to the tip of the plug. So this is indeed a mono socket. Clearly this socket will have to be replaced, and so I've assembled this. It's a stereo 3.5mm jack socket glued upside down to a small piece of strip board. its pins don't match up to a 0.1-inch grid, and even if they did, they probably wouldn't be in convenient locations, so that's why I've had to mount it upside down. I've wired it so that when it's fitted in place of the original socket, a mono or stereo plug inserted into it will have its tip connected to the audio output, and the new audio input can then be taken from the centre ring of a stereo plug, which I've wired to this header pin on the side. It won't matter if the input gets shorted to the output or down to 0 volts when a mono plug is inserted, as sometimes happens. In fact, a year or two ago, I went through all my supplies of spare and salvaged parts to find as many types of 3.5mm jack socket and plug as I could, and I experimented to see whether there's any consistency to what happens when a mono plug is put into a stereo socket or a stereo plug into a mono socket, etc. And I found, in fact, there isn't a standard answer. It varied depending on the design of the plug and the socket. Next is the question of which part of the Spectrum circuit should the new input be connected to. Now, the signal from the internal cassette player arrives on this connector here at pin 4 and is fed via this 680 ohm resistor to pin 34 of the ULA. On the other side of this page is a diagram of the circuit that's attached to that internal cassette player, and we can see that its output is generated by this audio amplifier here and fed to pin 4. That means that, of course, it would not be sensible to connect the new input signal directly to this point here, because that would mean connecting the output amplifier of the external audio player directly to the output amplifier of the internal cassette player, and that's rarely a sensible thing to do. So instead, I've been experimenting with feeding the signal from a Sony cassette player via a DC blocking capacitor into this point here. By doing that, I was able to get software to load, but it wasn't particularly reliable. I also had to turn the volume almost all the way to maximum. I know that this cassette player can generate an output signal of around about 5 to 5.5 volts peak to peak in amplitude. But once it's connected to here, that's reduced quite a lot, because the impedance it sees is rather low, mainly due to this 390 ohm resistor. Traditional cassette players can also usually produce a fairly high amplitude output, compared with many modern portable audio devices such as mobile phones, MP3 players, laptop computers, etc. And so using any of those things probably wouldn't be possible to load software. Now, on this circuit board, this 390 ohm resistor here is fitted on the rear of the board, and so seems to have been added as a last-minute design change. It forms a potential divider with this 680 ohm resistor, and I assume that was necessary because the output from the internal cassette player has too great an amplitude. So I have experimented with removing this resistor, and indeed it was then no longer possible to reliably load software from the internal cassette player. While looking at this diagram, I'll also point out that it probably isn't a very good idea to feed negative going signals into the ULA here, and so all earlier versions of Spectrum included a clamping diode from this point down to 0 volts to remove that negative going part of any waveform. So probably that's something you want to add if you're going to experiment with feeding an audio signal into this point. Even when software did load, it wasn't particularly reliable, it was rather error prone, and that this likely would not work with most modern audio devices, I think a slightly different approach is required. Here's an oscilloscope plot of the output of the internal cassette player while it was playing a software cassette. The centre horizontal line represents 0 volts, and the vertical scale is 1 volt per division. Clearly, this is not the audio signal as obtained directly from the tape. It's been processed, I would think by passing it through a Schmitt trigger or similar. The result is a well-defined square wave that doesn't go outside the 0 and 5 volt power supply rails. I imagine the ULA is easily able to interpret this as a logic signal. The amplitude of the signal doesn't change noticeably whether or not it's connected to the spectrum, and so the output impedance of the player must be fairly low. For comparison, here's the output from my Sony cassette player while playing the same recording. I've devised this circuit with the aim of converting the external audio input to a signal as similar as possible to that generated by the internal cassette player. It can also combine the external and internal audio sources. I've constructed and tested it on a breadboard and was very pleased to find that it works exactly as intended, and only a few minor component value adjustments were required. It's based around an LM358 dual op-amp. There's no special reason for this choice, it simply happened to be one of the first I found in a box of sundry spare parts. Going from left to right, it's powered from the computer's 5-volt supply. Because I intend to use a pair of header pins to connect the power supply to the final circuit, I've added Schottky diode D1 to prevent damage should the supply be connected the wrong way around. The external audio input is connected to the inverting input of the first op-amp via DC blocking capacitor C2. Resistors R1 and R2 hold the quiescent voltage at this point to halfway between the supply rails. C2 in conjunction with R1 and R2 forms a high-pass filter, with the 3 dB roll-off frequency at approximately 160 Hz. It wouldn't be a problem if this were a bit higher. My original design calculations called for a 7 nanofarad capacitor, but 20 nanofarads is the nearest value I had on hand. This is perfectly acceptable. The LM358 datasheet says it's safe for its inputs to be connected to voltages higher than the positive supply, up to 30-something volts. However, they should not be taken more than a few hundred millivolts below the negative supply. Schottky diode D2 protects the inverting input from such voltages should the output of the external source swing to negative. It should provide adequate protection from the types of devices likely to be plugged into this circuit. Most probably won't even be able to produce a signal of sufficient amplitude to ever cause D2 to conduct. The non-inverting input is placed close to halfway between the supply rails by resistors R3 and R4. This turns the op-amp into a comparator. The input signal is superimposed on the voltage at the inverting input, and as this swings above and below the voltage at the non-inverting input, the output snaps between the two supply rails, or as close to them as it is able to. Resistor R5 adds some positive feedback, turning the comparator into a Schmitt trigger. This addition of hysteresis means the circuit will ignore any low-level noise present on the input. If you don't know how this works, imagine R5 being in parallel with either R3 or R4, depending on the voltage at the output of the op-amp. This changes the voltage at the non-inverting input, creating two different switching thresholds. Not all op-amps work well or at all when used in this way, but the LM358 seems to be perfectly happy. The signal from the internal cassette player is coupled to the non-inverting input via capacitor C1. In the absence of any signal via C2, the inverting input is held at a fixed voltage, while that at the non-inverting input varies, and so a comparator is formed as before. It's a bit unusual to connect a signal to the non-inverting input of a Schmitt trigger in this way, and the internal cassette player probably sees some odd changes in the impedance it drives as the op-amp output switches. But the player's low output impedance and fairly large voltage swing mean this doesn't cause a problem. Of course, it isn't necessary to pass the signal from the internal player through a comparator at all, but it's an easy way to combine it with the external input. I did consider making the second op-amp a summing amplifier and adding the signal from the internal player there. All that will be required is an additional resistor. The second op-amp in the LM358 is used as a simple unity gain buffer. It probably isn't necessary, but it's present and so might as well be used. This circuit section also adds a small offset to the output, making it more closely match the signal from the internal cassette player, though I suspect this isn't important. Here's the oscilloscope plot from the internal cassette player again, and to its right, the output from this circuit, the blue trace, along with its input from my Sony cassette player, the yellow trace. I monitored this input at the junction of R1 and R2, hence the DC offset on it. I had the volume control of the player set to well below halfway, resulting in an output of not much more than half a volt peak to peak. I was able to turn it up from there all the way to maximum without any change in the square wave output of this circuit. This means it should be possible to use a wide range of audio sources. I hope you'll agree the output from this circuit is a very close match to that produced by the internal cassette player. Finally, Here's this circuit's output in blue when driven by the internal cassette player in yellow. Here's the circuit assembled on a piece of strip board. You might notice that I've run out of right-angled header pins, so I've had to bend over straight ones. Should you want to construct this circuit for yourself, then here's a diagram of the layout I've used. Let's see how it all goes together. You'll note I've mounted the new circuit on top of the RF modulator can. I did that by removing the lid from the can and making two small holes in it so I could feed a cable tie through. While I had the lid off, I noticed that the solder joint that connects the output resistor to the connector had cracked. Repairing that seems to resolve the problem of the intermittently fuzzy picture when using the RF output. I've also mounted the new dual-purpose input-output socket down here. I fitted that on a small bed of hot melt glue so the solder pins alone won't have to take the force of the socket being used. Now this short green wire here carries the new external input to the new Schmitt trigger circuit, and so that plugs in down here. Here's the cassette mechanism, and I've made a few changes to its wiring. As quite often happens to these, a number of these wires here were holding on just by one or two strands, so I've remade those connections and added a little bit of hot melt glue to reinforce them. I've also soldered on this new lead here that simply connects to the 5-volt power supply rails, and that plugs into the new circuit up here. On this connector, this pin here, there previously was a white wire that connected to this point here on the cassette mechanism. This is the output from the cassette player, which of course was carried straight into the spectrum here. I've replaced it with this yellow lead with a socket on the end, so if I want I can plug that into the header pin I fitted at this point here, and everything will work just as it did before. Or instead, I can plug the yellow lead in over here to the output of the new circuit, and this plugs into the spectrum. This lead here coming from the new circuit board is its input from the cassette player, so that should plug in here. I've used a screened lead for this, with the shield connected at one end only up here. Ideally, I wanted to use a screened lead for this cable too, but it proved to be rather difficult to connect the screen down here, and there wasn't a convenient way to do it here, so I haven't bothered. I don't think it would matter, but ideally that would be the case. Finally, of course, I need to plug in the voltage regulator, the thing I sometimes forget to do. There we go. Now let's switch the power on. First I'll test the internal cassette mechanism. If I connect the keyboard membrane, which I've removed from the upper case half, which is being cleaned, if I press the pad where the enter key will be and hold the contacts together over here, that simulates pressing enter, and the computer is now waiting to load. Of course, I have to lift the cassette mechanism off the bench while it's operating because of the moving parts underneath. Now I'll test loading using the external input. I've made up this lead, which should be suitable to use with this computer or a Spectrum Plus 3. This plugs into the back of the computer, and this flying socket carries the audio output, and this plug on the right the input, so that can be connected to a cassette player or a laptop computer, etc. I've used stereo connectors for both of these, with the signal connected only to the tip. That should achieve a sensible result when they're mated with either a mono or a stereo connector. The cassette player's volume control is set to the position I normally use with Spectrum computers, and that's at about 80%. However, with this new Schmidt trigger circuit, I should be able to vary it over quite a wide range, and that shouldn't have any impact on loading. In fact, so long as the volume control doesn't introduce any noise, I should be able to adjust it while the program is loading, and it shouldn't have any effect. I'm turning it down now. Yeah, I found the point just there where the circuit would no longer recognise the signal, but the controls turned down to about 25%, and a normal Spectrum certainly wouldn't be able to load from this cassette player with the volume turned so low. And so, as expected, I definitely think this new circuit should have no problem enabling the Spectrum to load software from modern audio devices such as phones and laptop computers.